Welcome everyone to the Bolin Centre Seminar Series, and this is a series we have where each of our research areas has a presentation throughout the year, and it's a great pleasure for me today to hand over to Schenk, who's one of the co-leaders of Research Area 5, to present today's speaker.
Thank you, Alistair. And usually we invite outside international, very well-known scientists to give the seminar here. But then this year we think, why not just us? Because us in the Bolin Centre, our scientists also doing very good science. So that's why we decided we invite our colleague Frederik come here for this first seminar in Bolin Centre Seminar Series. And just introduction for Frederik. Frederik got his PhD in 2013 in Hamburg University. Then after that, he did a postdoc in KTH, and then moved here as a research scientist in this geological science department. And last year, he joined us as RA5 co-leader. So now we have 3 co-leaders for our research area. And he is using climate model to do the paleoclimate modeling. And mostly, I think, focus on this transition period, abrupt transition for this late glacier. Last year, he published this paper on this Younger Dryas. I still remember that one of our master students even used that paper as an essay in one course. So then I told him, oh, you know this also is in our building. That he said, oh, maybe I know that. Yeah. So and after we experienced this very warm and dry climate last year, everybody I think have very much impression on that. So I think now it's a very good timing actually to think about this and put this kind of extreme weather in a long time scale perspective and understanding the mechanism behind. So very happy to have Frederik here today to talk about his modeling research on this topic. Yeah.
Thanks. I think I don't need it. Oh, no. Yeah, welcome everyone. It's a bit a sad start for that seminar because Wally passed away 2 days ago, and basically the topic I talk about to a large extent was also research he spent more than 50 years on. He basically was, I think, one of the first who proposed this great ocean conveyor belt, and that's one of his first figures. I mean, today it's more refined in terms of details, but in many ways he was completely correct already at that time. And I think he was a pioneer in many fields like radiocarbon dating, ocean chemistry, understanding ocean currents. And he also was already at that time when he understood actually that this conveyor belt is much more dynamic than previously thought. He also quickly understood the signals in marine sediment cores or ice cores from Greenland with this abrupt climate shifts in the past, that they are linked to this potential instability of that conveyor belt. And he was also quite concerned actually in terms of global warming, that this instability which we had in the past might actually show up again if the climate quickly moves to a different state. So I think he's really an inspiration for many of us. I think many of us also grow up with him during the studies with his papers, and I think he has one of the most cited books in ocean sciences. So yeah, well, that was a bit unfortunate timing for him to pass away just 2 days ago, but I think the topic somehow is really what concerned him, and somehow maybe it's not a coincidence that we are here today in his name also. So the topic today is late-glacial perspective on recent European heat waves. And actually I didn't really plan to give a talk about that, and also didn't really plan to do research about that. but there was a coincidence coming up for my late glacial research topics that all of a sudden they looked more and more similar to what we have observed in recent decades. And so I will give you today an overview about why it might be that the late glacial has some implications for understanding the current climate. And this comparison late glacial with weather or heat waves in recent time is very far away. And part of that knowledge that this can be linked is also related to studies by other people, especially about more recent things. So I will give you a brief overview first about recent publications related to the topic. And I forgot to mention what is interesting here in that figure. That's basically the difference of the last 4 years, the warmest 4 years on record, compared to the climatology. And what you see is the warming trend, but you have here a so-called warming hole. And that's something we know from the paleoclimate perspective. And the question is, of course, is this related to some unusual weather patterns over these years? For example, if you look a bit more in detail, you see here some kind of, in terms of the trends, of some kind of wave pattern. So if that would be the only explanation for that, then we could say, okay, there's something with an atmospheric wave train pattern, which was unusual during that time. And maybe to some extent, it can also explain this unusual cold SSTs. But it's actually not that simple. So I will briefly talk about this warming hole and show you how that might be related to European summer extremes. And second part, I will look a bit more at this warming hole. What does it actually mean? And is it a recent feature or does it exist over longer time scales? And in the third part, that's actually my real research area currently. I will give you an overview about results I get from looking at this kind of warming hole 12,000 years ago. And I do that mostly with climate models, but I started also to look more into proxy data because I mean, typically you say that the model needs to agree with the proxy, but sometimes I think it's also the other way around. So you have to also look sometimes if the proxy really shows what you think it shows. So I will talk a bit about that more. So first, I think everyone remembers the summer last year. And basically, it started to look a bit like that in the beginning. And somehow that was a reason why I thought, okay, wait, I have seen that now the last years. I have seen that 12,000 years ago, and now I see it again. And I looked a bit up what the literature tells us about that. And also looked actually just like more or less daily, looked at online on the weather data and also the reanalysis data. And that's basically how it started in May. We got here a high pressure center, very persistent, basically the whole month. And then you get, caused by that blocking, a very warm temperature anomaly, which is shown here in red. It's up to 4 degrees deviation from the climatology. And in the same time, you see again this unusually cold North Atlantic sea surface temperatures. And that's basically a repetition of what we have seen before. And to just get an impression how unusual the May temperature was in Stockholm, we are quite fortunate that Sweden has excellent long historical station data, like for Stockholm. And if you just sort the standard deviation of the warmest May, then you see that 2008, even no matter which kind of normal you take, is completely exceptional. And if you calculate a return period for that, then it would randomly occur maybe every 2,000 years. There's a huge uncertainty, of course, around that, but it just gives you a feeling how unusual that deviation is. And the whole summer was actually also unusual. So basically it started in May, and June and August were above average in terms of warming, but not exceptional. So basically the biggest deviation was in May and in July again. And if you look at Stockholm again, then you see here the time evolution of the May temperature in Stockholm, and then you see here the spike in 2018. June and August were not very unusual, but above average, and July was again extreme. So the return period of this outlier, let's say, is around 2,000 years, and here something above 200 years. And if we take all 4 months together, I think that was also what, I mean, somehow you notice that May was very warm, but somehow it never ended, this warming. And if you take these months together, some pop-ups here. Oh. So if you take the May-August temperatures together, then you see again that it's quite unusual. But you see already that at least some time here back in time, we had at least events which came close to this unusual warm summers. And I think there could be a own lecture about actually these warm temperatures here, and that should be given by Anders Moberg. He looked quite a lot into that data, and there's some indication that these warm temperatures are partly to uncertainties in how the people measure temperatures. But you see also in tree ring data that it was warmer during that period. So basically we know that it's very unusual, but we are also a bit uncertain how unusual it is in the long-term perspective. So I mentioned the warming hole, and some other people noticed that already before. And here's an example of Duché et al. I think that's the first paper I found about that topic. And she actually looked at the major European heat waves 92, 94, 2003, 2012, and 15. And she discovered that for all these events, we had this unusual cold SST here in the subpolar gyre region southeast of Greenland. And if she did a correlation between SST in May and July geopotential height, then she found that they are anti-correlated. So if the ocean temperature is warmer, then you get the tendency to have low pressure here, and vice versa. If you have very cold temperatures here, then you tend to have high pressure. So on that high pressure basically means a tendency to have atmospheric blocking over Europe. And that's shown here for the composite of June. It looks the same also for July and August. And so every time when you have this very cold SSTs, you tend to have this blocking anticyclone over Europe. It changes the position during different heat waves. So not every location has a heat wave every time, but Europe as a whole tends to have a heat wave every time we have very cold temperatures, at least since around 1980. And this could be still weather because these are just 5 events. There are some heat waves which didn't fit to that pattern. For example, 2010 in Russia, the heat wave was caused by a different reason. And so the question is if that is unusual weather or some ocean mode. There are several options. Maybe it's an anomaly in the North Atlantic oscillation. But if you look at longer temperature trends, which was, for example, done by Rahmstorff, he calculated the linear temperature trend since 1901. And here you see also that the warming hole basically has an opposite trend than the globe. So this is a long-term feature. And models, climate models, which simulate, for example, the pre-industrial and modern climate, they represent, if you force them accordingly with reanalysis data, for example, then they reproduce actually this fingerprint of cooling and warming south of it. And that's basically which created a new definition of the Atlantic overturning circulation. So because we don't really see what is going on in the deeper part of the ocean, the models confirm that you can actually use the SST deviation of that region, for example, as a difference to the northern hemisphere. And if you do that, then you can calculate an AMOC index just based on the surface temperature anomaly in this region. And if you do that, then you see that the blue part actually has a negative trend and the red has a positive trend, and the models and observations confirm that this is consistent with a slowdown of the overturning circulation. If that is applied, for example, to reconstruction of temperature from Michael Mann, and you calculate that index, you subtract the SST anomalies over the southeast of Greenland from the northern hemisphere mean, then you get actually an AMOC index, and that basically confirms that the AMOC slows down with more or less maybe the beginning of the end of the Little Ice Age. And here it's continued with observational data which actually confirm that the proxy is in line here. And if you go to the future, that's one example from for global climate model from Hamburg. Then you see that the AMOC index calculated as before from the surface temperature, and the AMOC anomaly from the ocean model in that case basically show the same. So that's a proof of concept that you can actually use that fingerprint as an AMOC index. And yeah, basically I forgot to mention, I mean, this AMOC slowdown, you see that in many scenario simulations for the future, but not all of them. So this is a huge uncertainty, and one problem with this simulation is actually that often they don't include, for example, meltwater from Greenland ice sheet. So this slowdown in the climate model is even without meltwater contribution from Greenland. So if you would think about rapid warming and melting of Greenland, it could be that the AMOC slowdown could be even stronger. But if you don't tell the model that, then of course it will not show up. So this is a slowdown without contribution from ice sheet melting. And if you ask yourself what is the response in the climate model to that slowdown in the overturning circulation, then there's one study from Harsmer. He did a CMIP5 model mean summer temperature change for one of the not so extreme future scenarios. And if you look at the differences compared to the modern period, then you see again here the warming hole here, and the response to that warming hole of the model ensemble is an increase in sea level pressure. So again, that would be a tendency to have increased atmospheric blocking during summer. And in addition, you have an absolute negative trend in turbulent heat fluxes, which basically contributes to stabilizing actually this atmospheric blocking. So what we have seen in the recent years is basically consistent with what models project for the future. So the question is now, how unusual is that, or can we rely on this kind of projections? And for that, I'll introduce now a bit to the paleoclimate perspective, very far away, 12,000 years ago. And some people might know that movie, Day After Tomorrow. That's basically a completely unrealistic, exaggerated case of AMOC collapse. So in that case, the ice age comes back, I think, what was it, days or weeks or so. But the beginning of that movie actually mentions many realistic aspects of this kind of events, but it's of course entertainment. So you should not take that too serious, but also you should not really ignore it. And the last time when we had actually this kind of, it was not a full collapse, but a partial collapse, That's called the Younger Dryas, and it's called after that plant which was found in Europe during that period, which is basically interpreted as a plant which likes cold temperatures. I learned now from ecologists that it's actually not true. They actually like light conditions, so they need a lot of light. So basically they spread because the trees disappeared, and then the interpretation is the trees disappeared because it got extremely cold. And that would be inconsistent with what I told you the whole time now. And yeah, I will resolve that. At least I work on that. So just give you a brief impression about the late glacial. Not everyone works on these strange periods, but here is an example of an ice sheet reconstruction of the last glacial maximum. This is basically the huge area here. And in pink, you see here the ice sheet during the Younger Dryas around 12,000 years ago. So it was much smaller, but still quite massive. And the elevation of that ice sheet is around here up to 2,500 meters. So in some cases up to 3 kilometers. So it's not only an ice sheet in terms that it reflects shortwave radiation, but if you run a high resolution model, it's also a huge obstacle. So what I found in my simulation is actually that the huge obstacle in terms of a fluid dynamical problem is more important than that the ice sheet is wide. We'll come to that. And the proxy compilations for this period, which are important for now, is that during this late glacial, that's the late glacial maximum 20,000 years ago, and that's the beginning of the current warm period around 11,700, is that the sea level was rapidly rising. In some centuries, you had an increase of up to 10 meters per 100 years. And Greenland proxy basically shows a lot of fluctuations in the temperature, and they show also this rapid shifts to warm periods and then back to cold periods. And you see here that this Younger Dryas is the last cold shift in that proxy. And you see also that the ocean temperatures during that period, the cold periods, are very cold, up to 5 degrees colder here, up to 2 and 3 degrees. Close to Portugal, and this is all explained by the changes in the overturning circulation. There are several proxies for that, and they basically show that the AMOC nearly collapsed in the so-called Heinrich I event, but it was still active during the Younger Dryas. The interesting thing is here you have a near collapse, and here it's still active. But in terms of Greenland temperature, the cooling was the same in both cases. And then the question is, of course, to which extent does Greenland temperature really reflect, for example, the full climate response to these AMOC changes. So there's difficulties in really quantifying how different these periods are. And it gets even more funny. If you run high resolution climate simulations for this different time periods, for this rapid climate shifts, then you have to take into account changes in boundary conditions. One important change is the change in summer insolation in orbital forcing. And today I show you only a comparison of two simulations. That's basically 13,000 Alaret compared to the mid-Younger Dryas 12,000. And that's basically the last cold shift. And the interesting thing is, if you compare, this is around 1,000 years differences, then you have here an increase in summer insolation of 5 watt per square meter. And that's quite a lot. If you talk about solar fluctuations in the modern climate, is 0.1 watt per square meter. So it's here around 5 watt per square meter. So on the one hand, the models, the coarse resolution models for the past predicted that it gets quite cold despite the strong increase in orbital forcing. And what I did now is I took from this coarse resolution climate model the ocean temperatures, which represent AMOC slowdown here for the Younger Dryas. And then I used SST from the strong amok state and the weak amok state, and used that as a horizontal boundary condition for the climate model. And just as a comparison what that means in terms of boundary condition, you see here the winter sea ice extend during the Allerette, so during a strong amok in the warm period, and the Younger Dryas, the sea ice extent goes down to northern Spain. And for the summer minimum, basically you have during the Allerette it's ice-free here, most of the Atlantic, and here you have still some sea ice. And this is now the boundary condition for the high resolution climate model, in addition to the sea surface temperatures. And the response to this drastic change in sea ice cover and ocean temperature in the high resolution, it's an atmosphere land model, and the ice model of the ocean is prescribed the ice fraction, but the fluxes of that sea ice are calculated by the new model simulation. So the SSTs are prescribed and the ice fraction, and the rest is fully coupled. And the resolution of that atmospheric model is around 1 degree, so 100 kilometers. And the surprising thing was that if you simulate that extreme cooling here in the ocean, then the model basically predicts cold monthly mean temperatures, except during June, July, and August. So that was a bit, first I thought that my simulations are completely wrong, because the expected outcome based on older simulation was that also the summers actually get extremely cold, or at least 4 to 5 degrees colder, and instead of getting colder in my simulation they get actually warmer. And basically that was a hard time to explain that. It's very easy to explain it in terms of physics, but it's not so easy to explain that in terms of the proxy records. So in terms of physics, it's mostly just a fluid dynamical thing. During most of the year from September, winter, and May, you have westerly flow. So if you cool down the ocean, you get cold air advected over Europe. But if you move into the summer months, then I don't show that here now, but the jet stream, basically the westerlies are quite weak in all simulations of the deglaciation. And then in addition you have the ice sheet which is blocking the westerly flows here, and then the westerlies get actually deflected to the north and to the south. So this direct advection of warm air actually is not possible anymore, because the air has not enough energy to go actually over the ice sheet, and that leads to atmospheric blocking by the ice sheet. But that's not the only reason. And an additional response I get is actually if I do a sensitivity simulation where I only change the ocean temperature but keep the orbital forcing constant, then this warming actually becomes even stronger. And that's basically indication that there's also a thermodynamic response in the climate model, and that's basically shown here in the sea level pressure. And here's a sensitivity simulation where I compare the 13,000 with the cooling in 12,000 but keep the orbital forcing constant. In that case, the cold ocean only leads to a strong increase in sea level pressure, which increases the blocking of westerly flow. If I add the orbital forcing, so the summer get more energy from the sun, then this blocking effect gets a bit weaker. So it basically tells you that the ocean is actually the dominant driver of this blocking and not so much the warming by orbital forcing. And this is now basically, if you remember, we have seen that in the future simulations, that if the warming hole here persists, then we get an increase in sea level pressure. And that basically is a similarity 12,000 years ago with well, the present and maybe the future. So this thermodynamic response, cold ocean temperatures can increase the atmospheric blocking in summer. And to summarize this results, it's basically 3 parts. It first starts that the amok gets weak, then you get this weak amok fingerprint, which was, for example, used by Ramsdorff, that you have this warming hole and here you have a warming. And basically, if you combine that in a simulation, then as a response, you get warmer summer temperatures. And that, even though today we don't have ice sheets, the mechanism is the same. The quantification is different. The changes at 12,000 years are much more extreme in terms of cooling, but less extreme in terms of warming. One reason is also that CO2 during that period is still much lower. So the difficult thing is now to align that with proxy evidence. And most proxies for temperature, at least in that time scale, are summer proxies in some way. Sometimes they are not called like that, but the reason is that most biological and chemical activity takes place in the warm period. So you have, if you have snow and frozen ground, then there's nothing going on. So the whole processes which somehow build up your proxies, most of them are somehow related to the warm season. And there are many different proxies, and I will only talk about a few of them. In the past, most of the July temperatures were reconstructed from insects. They are called, just classified as chironomids. And basically you find head capsula of this species in the sediment core, and there are some knowledgeable people who can identify them under microscope, at least at the taxon level. Another approach is to look in the sediment core if you find plant macrofossils, so plant remains which you can recognize from modern day. And for those, you know which kind of minimum July temperature do they need to actually grow or to migrate, for example. So you know if you find the plant, then it was at least as warm as the limit of that taxon or species. And the third one, I have not much knowledge about that. If you have questions, you have to ask Rink. That's branched GDTTs. And what I understood is somehow they built tetraeders which can analyze in the lab. And the size of the tetraeders somehow depend on the temperature. And then you can make a transfer function to calculate temperatures. So first, the old reconstructions, chironomids, we collected them for the different periods and then calculated difference for this warm period compared to the cold period, and they show that it's very cold here in the west and still cold here in Central Europe. If you do the same with the plant macrofossils, they don't show any cooling and indicate maybe even a slight warming. So the plants tend to agree with the model and the chironomids don't. And that was a difficult time to get that published. And we got actually 2 replies to our paper, but they got rejected from the editor. So maybe there's more to come, but the main problem they have is actually that, well, first of all, they don't like that our proxy doesn't agree with their proxy. And the second thing is that these plant macrofossils, you only find them sometimes in the sample. So if you have 1,000 years in one core, maybe you find them every 200, 300 years. So they don't really give you a robust estimate about the climate variability over time, but they somehow indicated that during this cold Younger Dryas, they were actually still there. So we have some indication that these plants still were doing fine in the cold period compared to the warm period, but we could not exclude that part of that 1,000 years was actually colder than indicated by that proxy. And another thing which they don't like is that they think we should use much colder thermal limits for the plants, because some plants grow, for example, in mountain areas in Norway, in the Alps, at much colder temperature. But the problem with these proxies is actually that they typically grow at a southern slope. So although the air temperature there might not be as warm, they get direct solar insolation. So somehow we use a calibration from Finland, which is on a plain, relatively flat terrain, and there you can be sure that the insulation, because of the slope, is not really the driving factor. So it's really the thermal limit of that plant species in terms of temperature and not of solar radiation. But maybe we are still wrong. I don't know. So far, I have not really seen that they falsify the proxy. And we have now the problem that we have two proxies and two options. So chironomids agree very well with the cooling pattern in May, so where we still have westerlies, and the plant macrofossils tend to agree, maybe not with the warming, but at least they say it didn't get colder. And what you could do now is actually you go back to the coarse resolution models, which have done previously, and then the chironomids would also fit with the July temperature. So you could say that my model is an outlier and the coarse resolution model is maybe doing a better job because it agrees with that proxy, but then it would not agree with that proxy, and even worse, the coarse resolution model just doesn't agree with the basic fluid dynamics around the big obstacle. So I skipped most of that. I just want to show that for different regions, these differences between the different proxies can be quite extreme. And I'm working on actually understanding why the chironomids are so cold. And one reason actually why they are so cold is that they are calibrated in an oceanic climate. But actually the climate at that time is very continental, so we repeat actually now this reconstruction with a continental training data set, and then these differences get actually much smaller because in the continental climate the species don't show such a cooling anymore. And this is basically one example from southern Sweden, from the site is called Hässeldalar Port. I think it's one of the most studied records maybe of Sweden, together with another lake in Attershep. And for that we have a lot of different proxies. I show only some examples. This is now the July temperature from this chironomids as a time evolution, the warm period called period warm period. And here you see the strong cooling and new data. This is unpublished from these GDDTs. They actually don't agree with this cooling, and even more interesting, whenever the chironomids show very cold spikes, they indicate very warm spikes. And if you remember the model, that there was a cold ocean, warm summer feedback in the model, then it could be that this is a lucky shot that actually these proxies represent that. But we have to be careful because it could be much simpler. Maybe we just got some erosion events where you get, for example, GDTs from the warmer soil washed into the lake, and then you think that the lake is actually warmer. So there's some uncertainty about that, but there's also some more evidence that it might actually make sense. And here show changes in total tree pollen from that lake. And what you see here is when you get that cold spike in the chironomids and the warm spike in the GDTs, the trees are still doing fine. So somehow they are from the same core. They didn't respond to that cooling. So the cooling was maybe not the reason why they disappeared, but after this warm spike, then the tree pollen go down. So it could be that not the cooling was causing them to disappear, but maybe rather hot and dry conditions. And there's another option, if you look at Artemisia pollen, also from the same core, they typically expand when trees disappear, and also they like very dry conditions. So basically when the tree disappears, then the Artemisia increases, and also they tend to agree actually with some of the hot spikes in the GDT. So that could be an indication that we had some kind of tendency to have more paleo heat waves or droughts during that Younger Dryas, which actually always seems to occur when the chironomids are quite cold. And that could be an indication that this warm, cold ocean, warm summer mechanism actually exists. But it's still a long way to go because you need also to look at other lakes to confirm that. And I didn't really talk much about droughts and humidity, but it's quite obvious if you make the ocean very cold, you get much less evaporation. So based on Clausius-Clapeyron, you can say 1 degree cooling, 7% decrease in humidity. And it's not surprising that then the response to a weak AMOC and a cold ocean is actually that it gets very dry. And we work actually with people who do hydroclimate proxies, but there's a high likelihood that they will give a presentation during this year here, so I'm not going to talk about that. So I'm finished. That's the summary. Basically, well, there are some suggestion how this cold ocean warm and dry summer mechanism could look like. So in the Younger Dryas, maybe in the present and the future, you can have a cold ocean in the North Atlantic because the AMOC is slowing down, or for example, if you get more meltwater from Greenland ice sheet. And then the model tells two things. The cold water leads to a thermodynamic response, so an increased tendency to have atmospheric blocking. And the other thing is that the cold ocean leads to less evaporation and therefore to less precipitation. That's basically what I was talking about. And the third thing, the late glacial is different from today because this blocking in the late glacial is additionally enhanced by the ice sheet. So an uncertain question is to which extent this mechanism applies in the modern climate. It does in the models in terms of that you get a response in the sea level pressure to the cold ocean, but the models fail to actually really simulate atmospheric blocking, and that's a big problem of current model development. So you cannot really test this in a very realistic way in terms of really quantifying it. And what I didn't talk about, but which is basically a chain of command, if you have this kind of thing, is that the thermodynamic blocking leads to deflection of westerly winds. You get higher solar radiation, less clouds. Then you get less soil moisture, and then you get a positive feedback because evaporative cooling does not really work anymore. And over time, during the summer, then you have less evaporative cooling, and you have the risk to have severe heat waves and drought at the end. And these heat waves would be based on CO2 warming and so on, would most likely be more extreme in the modern climate, while in the late glacial, low CO2 levels would mean that these heat waves are actually not as extreme as in the modern world. So that's basically the perspective on this heat waves from a paleoclimate perspective. Thanks a lot.
Thank you very much for this great talk. And now it's question time. Any questions?
Tendencies continuous.
Oh, yeah. Otherwise they don't hear you. Yeah.
Are these tendencies continuous? It seems that 2018 stands out, and if you have a slowing down of the AMOC, wouldn't you expect it to happen successively during the years?
Well, that would be the worst case if this warming hole becomes a persistent pattern somehow, and this response has a strong impact. Then there would be an increased probability to have more extreme heat waves or droughts. I mean, it will not be in every year because you still have chaotic weather systems, and sometimes other factors are more important. But I mean, the period since the 1980s basically tells us that there's already quite a lot of events which are, all of them were very rare somehow, but we had now so many of them, so it could be that these are not random events anymore, but maybe they have a forcing by the SST. That was basically the study from Deshay et al. 2016. She showed that there's a correlation between this SST region and the sea level pressure and pattern over Europe.
Because my impression is that you have a very great variability in the climate from year to year.
Luckily,
and this 2018 stands out very much.
Yes.
Also compared with earlier hot years.
To some extent, I mean, it stands out for especially Scandinavia.
Yes.
And I think the 2003 heat wave, which had a similar SST pattern, was more extreme, for example, in France and parts of Switzerland and southern Germany. So these extreme events, this high pressure blocking is not always at the same place. It can be sometimes over Scandinavia, sometimes more over Great Britain. And depending where this blocking sits, you get a heat wave at a different place. So, but the frequency to generally have this unusual heat waves over Europe basically seems to be a tendency. So it doesn't mean every time Stockholm, but basically Europe. Yeah.
Thank you.
Oh, David.
Yeah, I'm just wondering, what are some of the reasons that current models are not getting this kind of blocking behavior? And could you take your model and possibly simulate a 2018 style event?
If I would know that, then it would be good. Yeah. But I mean, nobody knows. I mean, for a long time, there was the assumption that the model resolution, I mean, if you have a coarse resolution model in terms of the atmosphere, the blocking is even worse. But now, even if extremely high resolution modeling, the blocking improves, but it's still far away from the observed blocking frequency. And I'm not aware that any model is really realistic in that case. And there's also no theory about how that atmospheric blocking really works. I mean, there are a lot of explanation, but the problem is that the reasons which cause the blocking to start are maybe not the key reasons which the key which makes them persistent. So it could be different effects, and one of them somehow doesn't really work in the models. And there's also observations, or basically also calculations, that actually the high pressure blocking is also influenced by the cyclones. So it could be that some of the process related to cyclones actually lead to unrealistic blocking. So it's very complicated, but I don't know how to resolve that. If anyone knows, I think he will win a prize for that.
Yeah, more questions?
Have you seen anything on the Rossby waves?
You mean now in the modern time, or the back in the late glacial? Yeah, I mean, in order to have blocking, the Rossby waves look different. I mean, the jet stream basically starts to have more meridional excursions, and over Europe, typically during blocking, you get actually a split of the jet stream. So one part goes to the north, the other goes to the south, and that's also similar which you get in the late glacial in response to the ice sheet. So, but what we don't really know is what really affects the jet stream to stay in this kind of wobbling mode. And one theoretical or also plausible explanation is actually, for example, that the Arctic amplification plays a role, because the theory of the Rossby waves or the jet stream is basically that you have a strong gradient between the warm tropics and the cold Arctic, and the stronger this gradient is, the stronger the jet stream. And because the Arctic is warming more rapidly than the tropics, this gradient decreases, and therefore also the jet stream should slow down. And when the jet stream slows down, then it starts to have these excursions. I think theoretically it's plausible, but the thing is that the model don't really do it. So that's why you see here these nice figures and not real model simulations, because it doesn't really work. So, but you see it in weather models. So if you use reanalysis data, there you see this kind of blocking situations. So.
And I have one question about this. When you have this kind of scale via ice sheet, this mechanic forcing actually is constant. So do you expect that you will have more persistent warm summer during Younger Dryas? When you have this, because you said this mountain is more important in your simulation.
Yeah, I mean, well, I'm planning to actually do a simulation where, for example, remove the Fenris Canyon ice sheet in the Younger Dryas and look if I would still get this kind of blocking in response to a cold ocean. Because it could be that just lucky somehow, because the ice sheet somehow does already some blocking, and then the thermodynamic blocking can combine with that. And the question is, of course, is that still working without the ice sheet? But that's I don't know so far.
Because I think it will also cause some feedback because
Yep.
we have warm summer, then you will melt in this ice sheet.
So in that way you mean. Yeah, that's actually an interesting thing because I think I didn't include the figure. But if you look even more, zoom in on the ice sheet, on the wind pattern over the ice sheet, then you see actually that is at the lowest wind level you get this typical katabatic wind system. So basically the ice sheet at the lowest level the model creates its own wind pattern, and that's sometimes even not aligned with the higher wind pattern. And that pattern tends, because of Coriolis rotation, always it gets a tendency to have easterly winds coming from the southern part of the ice sheet. And if you think about ice sheet melting, this should actually mean that you should have a lot of ice sheet melting during summer. But the other thing which I didn't talk about is that during winter, the high resolution model gets much more cold than the coarse resolution model. For example, the Younger Dryas, the coarse resolution model predicts winter temperatures of around minus 20 degrees. And in my case, it goes down to minus 45. So then the question is who wins, the winter cooling or the summer melting? But I think that would be your own project, and I need ice sheet modelers for that.
Thank you. More questions? If no more questions, we close this seminar, and thank you very much for this talk.
Thank you.